If a tree falls in the forest and there's nobody there to hear it, does it make a sound? Philosophers have debated this classic problem through the ages. For psychologists, though, it's less of a problem. The way we see it is that the falling tree generates vibrations in the air, but it is our brains that detect those vibrations and convert them into what we understand as sound. Sounds is what we hear, and if nobody were there to hear it, there would be no sound. Except, of course, the other animals would be there and they would be able to hear the sound of the falling tree. Hearing is our second most important sense. If we cannot hear, or if our hearing is impaired in some way, it can affect us a great deal. Hearing loss makes us feel cut off from other people and not a fully part of what's going on around us. And that is why we regard hearing aids, sign languages, and other forms of support for deaf people as so important. Hearing is a significant part of the way we communicate with other people. And it's also important to keep track of what is going on around us. Sounds are the impressions we experience as results of vibrations carried through the air or through water if our ears are underwater. We humans can recognize a range of sounds, pitched intense sounds and which have higher frequency vibrations to low booming sounds with low frequency vibrations. But as with light, other animals can detect signals beyond the extreme ends of human hearing. Bats, for example, can produce and detect much higher frequencies than humans can. So a bat in flight might appear to be silent when in reality it is shrieking out high frequency calls and listening to their echoes. At the other end of the spectrum, whales produce calls that are so low as to be undetectable to the human ear, but which travels through the water across vast distance and can be heard by other whales hundreds of miles away. On land, elephants communicate in a similar manner, using infrasounds that are too low to be detected by human hearing but which other elephants can hear over large distances. Now, making sense of the changes in air pressure around us isn't just about identifying frequencies. We also detect how loud a sound is, and it's conveyed by the amplitude of the pressure waves that reaches us. Um, Loud sounds produces waves with higher amplitudes, while quieter ones have lower amplitudes. Sounds are also complex in that most of the noise we hear consist of several elements mixing together more than one frequency. Pure sounds of just one frequency are very rare both in nature and in everyday life. The sound of the flute is probably the closest we come to hearing a pure tone. That is, a sound produced by just one single frequency. But it is a combination of frequencies which gives sound the identifiable characteristics. We learn these characteristics effortlessly. In some cases, almost from birth. We are particularly sensitive to voices which we can easily distinguish from other sounds. Everyone's voice has a distinctive mixture of frequencies, which means that we can quite easily tell one person's voice from another. And human infants can distinguish the voice of the people looking after them from just a few days old. Now, the auditory cortex of the brain is also super sensitive to timing of sounds, much more so than the visual cortex is to the timing of visual stimuli. We can tell how close together different sounds or the elements of different sounds are even when they are closely timed. This is completely different from our visual system, which, as we have seen, tend to merge together stimuli that arrive rapidly. With sounds, the combination of frequency, amplitude, and timing of signal means that we are processing quite a lot of information from the vibration in the air around us. In this video, we are going to talk about how do we hear, and also making sense of, or making sound make sense. We will also talk about how we hear speech and music. Of course, our story starts with our ears. Have you ever noticed how sound seems different when we hear them through headphones? That's because they are coming directly into our ears without involving the outer ear. In particular, the upper part, which is known as the pinna. The shape of the pinna directs sound inwards, and that helps us to judge where the sound is coming from. Everyone's ears are slightly different, so there are small differences in how the sound is channeled inwards, and our brains are sensitive to these. Researchers investigating those differences have made models of the shape of the pinna and recorded sounds using microphones placed in those models. They also recorded other sounds without a pinna shape. Now, and they played both types of sounds back to their research participants. People were much more accurate at judging where the sound was coming from when hearing the sound recorded as if they are received by a human ear. And they were more accurate of all when judging sound recorded from a model made from their own ears. Now, the vibration of the ear receives are very small, so they need to be amplified before they are converted into signals the brain can use. We do this using a set of small bones in the middle ear known as the malleus, insus, and stapes. These are Latin for hammer, anvil, and stirrup. Here we can see how the brain or how the ear is structured. Sound waves are collected by the pinna. Sound waves are collected by the pinna and focused on the eardrum or tympanic membrane. Now, these sound waves make the tympanic membrane vibrates like a drum. The vibration are picked up by the malleus bone, which amplify them a bit, then passes on to the insus, which amplifies them a little more, and then to the stirrup, which does the same. Now, the stirrup is in contact with another membrane known as the oval window, and by this time, the vibrations have become larger and more detectable. The oval window passes them onto the inner ear, which is filled with a fluid called perilymph. Fluids doesn't squash as easily as air, so there's another membrane lower down called the round window, which moves in and out to compensate for the pressure caused by the movement of the oval window. Now, the purpose of the ear then is to collect sound waves and amplify them, but the brain, as we know, works on electric impulses and not pressure. So the next step is transduction, converting sound waves into electrical impulses that can be passed on to the brain. This is what happens in the cochlea of the inner ear. The vibrations from the oval window push the fluid, causing the membranes of the inner ear to vibrate in their turn. Now, a series of hair cells on one of the membranes, the basilar membrane, respond to the vibrations by generating an electrical impulse. Now, not all the hair cells respond in the same way. The hair cells at one end of the basilar membrane are more sensitive to higher frequencies of vibrations what we experience as higher pitch sounds, while the other end is more sensitive to lower frequencies, and the ones in between respond to middle range frequencies. This means that the sound we receive will stimulate different cells to produce electrical impulses, depending on what the sound is like. Now, the hair cells make connections with a set of neurons with very long axons. This bunch together and form the auditory nerve. And the auditory nerve passes the information now in the form of electrical signals to the brain. So, as with vision, much of the incoming information is sorted before the signal actually reaches the auditory cortex, the part of the brain that makes sense of what we are hearing. Now, the auditory nerve has its first synapse point to in the thalamus at a group of cells at the known as the medial geniculate nucleus. From there, the information goes to a group of cells found at the side of the brainstem known as the cochlear nucleus. This is where the sound frequencies are identified. The upper parts of the cochlear nucleus receive information about high-frequency sounds, while the lower part receives information about lower frequencies. And a sound of intermediate pitch stimulates cells in between. We find some sounds relaxing, and as a rule, these tend to be the middle ranging sounds. Other sounds, though, we find quite disturbing. We react more strongly to a scream, a high-pitched sound, than we do to mid-range hum. And we also react to some kind of low-frequency sounds. Think of the shark theme in the Jaws movies, for example, or the sound of a lion's roar. So we can see that our ability to distinguish high-pitched sounds from lower-pitched ones could have real survival value, which may be why it is one of the first things that the brain processes. Being alerted to potential danger is all very well, but we also need to know where the sound is coming from. So some of the nerve fibers coming from the cochlear nucleus go to the pons, which helps us to understand the direction of a sound source. They go to a part of the pons called the trapezoid body, which form a crossover point for the auditory nerve fibers, a bit like the optic chiasma, thus for our vision. Now, like the optic chiasma, half of the nerve fibers carrying sound information cross over to the other hemisphere, and half stays on the same side. This means that the brain can compare the slight differences between the sound coming from each ear, which helps us to work out where a sound is coming from. Now, the next step in the auditory pathway is also in the pons, at a part called the superior olivary complex. Here, the information is sorted even more, beginning to give us some of the richness we experience. One side of the superior olivary complex processes loudness, with some cells responding to high amplitude vibrations while others respond to quieter sound. The other side of the superior olivary complex is all about timing, with some cells responding to rapid repetitions of sounds and others to single notes or calls. Once it has been sorted for these basic characteristics, auditory information passes to the cerebrum, to the auditory cortex on the side of the temporal lobes. That is where our conscious hearing is processed. These aren't the only connections. These aren't the only connections. Sound information many other connections with other parts of the brain as well. But what I have described are the main pathways. Because of the route that the information has taken, the signals that the auditory cortex receive include information about pitch, loudness, timing, and the direction of a sound or that a sound is coming from. All of these contribute to our experience of sounds. The task of the auditory cortex and the other brain areas associated with it is to make those sounds make sense. Pitch, as we have seen, is fundamental to how we interpret sound. And in the primary auditory cortex, the central area processes low-pitched sounds, while the other areas processes the higher pitches. Now, this makes the what researchers call as a tonotopic map. That is an area that responds to different pitches in different places. But the rest of the information shapes what senses or what sense make us from the whole sound. Now, the auditory cortex, as seen in this diagram, is generally organized into three areas: the core, the belt, and the parabelt. Now, the core is the area, or rather is the primary auditory cortex, which responds to specific features of the sound. Now, it contains specialized neurons which collects from neurons responding to single frequencies and in their turn respond to mixtures of frequencies. This in turn feed information to other neurons. Now, some cells, for example, respond to voices more actively than they do to pure sounds. Other cells respond only to changes in frequencies, but not in the frequencies themselves. And some neurons respond by becoming active in response to specific frequencies, but switching off and becoming inactive when stimulated by a similar but not identical one. Now, it's all a bit like the simple, complex, and hyper-complex cells of the visual cortex. But the response is to the qualities of complex sounds rather than visual shapes. Now, the belt area, as its name suggests, goes around the middle and goes around the middle part, goes around the middle, and it's the part immediately surrounding the core, and it seems to do two things. The frontal part codes the content of the sound and passes the information onto the frontal and parietal lobes of the cerebrum, and the back part of the belt region, known as the planum temporale, works out where the sound is coming from. It collates the information from the trapezoid body with the information coming from the distinctive shapes of the pinna. So, neural processing in the belt area helps to tell us what we are listening to and where the sound is coming from. Now, the belt area of the auditory cortex merged into the outer area, the parabelt, which deals with more complex functions of hearing. One of the things it helps to do, for example, is to identify and interpret speech, which we will look at next. But it has other functions too. It's connected with auditory working memory, which is the way you carry the immediate memory of a sound in your head while you are thinking about it. With linking together auditory and visual information, and with making connections with our memories of other sounds. Now, if the primary auditory cortex is damaged on just one side of the brain, we experience some hearing impairment. So we don't hear so well and have difficulty locating sounds. If the damage is on both sides, though, we experience full deafness. That deafness is not the result of sound being undetected. It arises from the fact that the brain can't make sense of them. As we have seen though, sound information has already been processed to an extent before it reaches the cortex. So people with this type of deafness can react emotionally or reflexively to sound. They might show startled reaction to a sudden loud sound, for example, or be emotionally disturbed by loud cries. What they can't do is to describe in words what it is they are reacting to. As to blind sight, they experience the feeling but not the perception of the stimulus. The auditory cortex has many connections, but it links with other parts of the brain through two main routes. One of them, known as the what route, is all about identifying specific sounds. It's the way we work out what we are actually hearing. It's sometimes known as the ventral stream, and it passes along the lower side of the auditory cortex and the front or anterior part of the temporal lobe. The other is known as the where route, and as its name suggests, it's about locating where sounds are coming from. Now, it passes along the upper or dorsal side of the auditory cortex, so it's often called the dorsal stream. This neural pathway makes connection with motor parts of the parietal lobes and the frontal cortex, preparing us for movement, among other things. But of these routes, of course, are equally important in helping an individual to survive. But there's more to hearing than this. Let's also look at some of the more specific things that we listen to. Since the 19th century, scientists have been aware that the left hemisphere of the brain is more important for language and speech than the right hemisphere. It isn't totally exclusive. The right hemisphere does have some simple language functions, and some studies of people who have had their whole left hemisphere removed have shown surprising recovery of language functions. Not just conversational speech, but also memories of songs and stories. So it isn't as simple as left brain equals language or right brain is equal to music, but then it never was. Have you noticed how easy it is to tell the sound of voices from other sounds? We can distinguish speech from other types of sounds even when we can't make out the words. Part of this has to do with learning. We become familiar with the speech with the speech sounds called phonemes used in our own language, possibly even before birth. Different language use different phonemes, and we may not always recognize those particular sounds as part of a particular language, but we can still recognize speech when we hear it, even with unfamiliar phonemes, because we are also familiar with the typical timing and pattern that people use when they are speaking. Anyone who has known a small child will, while they are learning to speak, will have seen how they often get the pattern and timing of speech exactly right, even while the words they are producing are still on only babble or nonsense sounds. This comes to a point in our processing, or there comes to a point in our processing of sounds where we differentiate between speech and other types of noise. Functional imaging studies show us that both sides of the primary auditory cortex respond equally to speech noise and other types of noise. But then, the what pathways begin to distinguish between the two. Speech sounds produce more neural activity in the left temporal lobe than they do in the right temporal lobe, while the right temporal lobe responds more strongly to changes in pitch, particular to musical ones. There is activation in the opposite sides of the brain, opposites of both, but it isn't as strong. Now, the what pathway branches again as it leaves the primary auditory cortex. One branch passes through the anterior temporal lobe, connecting with a speech recognition area below the primary auditory cortex and going on towards the frontal lobes. On the way, it passes through an area that deals with knowledge of words and meaning, and another area that is involved with the planning of speech. The other branch goes towards the back of the temporal lobes and make connection with areas which also link with the visual system, with an area known to interpret gestures and other concerned with the reading. So while both branches are connected with what the signals are, as opposed to where they are coming from, the first branch is concerned with the mechanics of how speech happens, while the second is concerned with meaning. Together, they allow us to understand what people are saying when we listen to them talking and watch them as they do it. Now, making sense of what we hear has everything to do with the timing of sounds as well as the sounds themselves. This is particularly apparent when we consider how we respond to music. Early advertisements from the gramophone, dating from the first half of the 20th century, described it as the musical instrument everyone can play. In modern life, we are surrounded by music in just about every sphere. And it's easy for us to forget that this is relative recent happening. Until the advent of popular and affordable recorded music, most people's exposure to music was very limited. Unless they were very lucky to have an instrument at home and the skill to be able to play it, most people's experience with music was only what they have heard at fairs, concerts, and other social events. Yet we all have always responded strongly to music, and it has always been an important part of human society. Weary and wanting to recover from her domestic cares, Meg Brooke in the novel Little Women asked her husband if they can go to a concert because I really need some music to put me in tune, showing how music can relax, soothe, and calm us down. It also can also have the opposite effect, of course, as composers of film music are well aware. But we all appreciate music naturally. Even small children enjoy hearing music. And some researchers believe that music perception is as strongly built into the human brain as the ability to use language. We can think of music as being patterns in time. Our vision is sensitive to patterns in light. Our hearing is also sensitive to patterns, but since sound is ephemeral, we receive the pattern in how notes combine or follow one another. As we have seen, the auditory system is far more sensitive to timing than the visual system. And timing is an essential part of music. Judging by the effect of lesions in particular areas, the right hemisphere is more concerned with processing information about pitch, while the left hemisphere possesses information about timing. Unlike the popular myth, both cerebral hemispheres are involved in music perception, but they generally focus on different aspects of the phenomenon. In fact, it's generally considered that music has its overall positive effect because it stimulates areas across the whole brain, rather than just one or two parts of it. You'll have gathered from this that music processing is quite a complex affair. Brain imaging studies of people listening to music shows activity in the auditory, motor, and limbic system. Or rather at its simplest level, the auditory system is processing melody, the motor system is reflecting timing, although we know that timing is also processed in the auditory system, and the limbic system is responding to the emotional nuances of the music. Incidentally, this imaging studies found similar effects regardless of whether people were listening to pop or classical music. Music can also help our general brain functioning. Studies of older people found that they showed faster neural processing and a better memory for events as a result of listening to music. Like language, music can take different forms in different cultures, but it always tends to be based on a set of discrete pitch levels. What we think of a musical notes clearly as a musical note are clearly separated. Now, the range of possible wavelengths in between is regarded as off true and not appropriate for music. While musical pitches are generally arranged in octaves, what counts as an octave can vary from one musical scale to another. Western music, for example, usually use a heptatonic scale, which with 7 notes in an octave. But there is also no single universal scale. Older Celtic and Gaelic tunes often use a pentatonic scale based on 5 notes, for instance, and as does much Asian music. And some supposedly primitive but actually very sophisticated music is sometimes based on scales of just 4 or even 3 notes. Now, these scales are not random. The way the notes are grouped is based on the properties of their sounds as processed in the auditory system. Some combinations just feel right. Some notes seem to follow other naturally, and those impressions come from a combination of the acoustic properties of the sound and the cultural experiences of the individual. It's not that we don't perceive the frequencies between the notes. As we have seen, speech perception involves subtle nuances of pitch, not limited to the tones which are part of musical scales. It's that they don't seem to fit they don't seem to fit properly, so they sound wrong in the context of the music. Amusia is the inability to process music. It can happen as a result of brain injury or disease, but some people have congenital amusia. Amusia. It is that is they are tone deaf and unable to sing accurately or produce music themselves. They can still distinguish frequencies though, because they are still able to copy pitch shifts in speech. People with amusia are more sensitive to speech tones than they are to music. Being tone deaf is associated with the density of gray matter in the right hemisphere around the auditory cortex, but it doesn't correlate with any other known brain deficit. However, brain plasticity studies show us that the amount of gray matter can reflect our experiences. So the fact that there are less gray matter in these areas could have resulted from the fact that those people simply don't engage with music as much. In other words, it could be a result rather than a cause of the amusia. We will learn more about it as research in this area continues. Most people have some experience of performing music, even if it's only singing along to a favorite song in the car or joining joining in basketball chants or how do you say that? Uh, or cheer dance. So, singing, of course, combines our knowledge and processing of speech with our knowledge of music. And even the simplest level of singing requires the brain to exercise control of timing and pitch. Even tone deaf people can respond to musical timing. It's quite usual to tap one's foot to a beat or clap along with some kind of music. Now, this reflects the strong connection between auditory and motor processing. The fact that we don't respond in the same way to rhythmical visual input, like say a video of a ball bouncing, shows us how strong the connection is. It also shows us why dance is such a powerful and universal part of the experience of being human. The close links between the movement centers and the auditory processing areas of the brain give us a powerful tendency to respond to rhythmical sound with movements. It's inbuilt and universal. All human cultures, no matter how remote, have some tradition of dance and music. Dance connects our auditory input with music, with muscle action, and also with input from the part of the inner ear that gives us our sense of balance. Moving to music comes naturally to us, but some forms of dance are more complex. As with our physical skills, as we practice, we become better at it. And that practice develops neural connections in the brain. Studies have shown that the combination of mental and physical exercise involved in dancing can sharpen our problem-solving abilities and working memory, as well as helping us to keep fit. Whether it's dancing or playing a musical instrument, performing is doing. But when we think of musical performances, we are generally talking about something much more sophisticated than just tapping our feet to a tune. Playing an instrument like a piano requires the brain to connect a spatial activity, choosing which specific key to press with an auditory stimulus, the note, in a way that is precise, unthinking, and rapid. This means that a pianist has to forge more or less automatic connections between the motor cortex, the cerebellum, and the auditory cortex, and also the frontal cortex, which is involved with planned actions and decision making. Brain scans of professional musicians shows that their brains have changed in response to their years of continuous learning. They have large areas in the motor cortex as a result of their extensive physical practice, and larger and more symmetrical auditory areas. Trained musicians also process music differently in the brain. For ordinary people, listening to music mainly but not entirely involves the right hemisphere of the cerebrum. When trained musicians listen to music, though, both hemispheres are active, and the left hemisphere is often more active than the right. Professional musicians also have a more developed corpus callosum, the band of fibers connecting the two hemispheres and passing information from one another. We know that the left hemisphere is more concerned with computational activities, and it may be that musicians bring more formal knowledge to their listening than an ordinary person because they are familiar with musical syntax. While a trained musician will be unconsciously analyzing the music they are listening to, a non-musician will simply be experiencing the music without analyzing it. Timing, as we have seen, is an essential part of music, and it is part of the things that musical training focuses on. People who are musically trained are particularly sensitive to timing and have been shown to process all sorts of auditory information more quickly as a result. Very quick speech, for example, requires rapid neural responses in order to decode it, and so does other fast auditory input. Older adults quite often find difficulty in the neural processing of this type of input as their brain cells respond more slowly, but trained musicians don't suffer from this problem, nor it seems to do people who had some musical training when they were children. Now, a study by um, White Shoe compared older adults who had learned an instrument in childhood with others who had not and who had not had any musical training. Even those who had given up playing as they got older showed faster neural responses to speech than those who had never learned. It seems that the benefit of music education can stay with you even 40 years later. Now, hearing is a complex sense that is an important part of our experience of being human. Together with sight, hearing allows us to detect, identify, and respond to the world around us. In this video, we've learned that sound information is collected, amplified, and transduced into electrical impulses by the ears. It then passes the thalamus and the auditory cortex. Now, the center of the auditory cortex codes the information while the belt areas works out what and where it is, and the parabelt connects it with memories and other senses. We are particularly primed to detect speech and can easily recognize the sound of voices above other sounds. We are also powerfully primed to respond to music. Each culture has its own musical tradition, but our hearing system learns them easily. Both sides of the brain process music, but in different ways. So this ends our video for this week. Again, my name is Dex Kamitan, and thank you for watching.